If we focus on the streamline of the flow, we can observe that the velocity is much smaller than the case in at the microgravity, normal gravity, because of the thermal heat loss is expanded, which leads to a expand time scale associated with the transport and the combustion process. So as this configuration allows us to further understand the physics behind, it will be also applied to for the flare project with the experiment aboard ESS in 2023. All the experiments are conducted in this experimental rig diamonds. Here, the schematic shows the combustion chamber. Three controlled parameters are the pressure, flow velocity, and the oxygen content. The samples are fixed in the center of the combustion chamber, and experiments are recorded by an infrared camera and a CCD camera. And also, a uniform backlighting at the back of the sample in the direction of the CCD camera is set alternatively on and off during the image recording, so that the solid surface of the solid fuel surface and also the release, the smoke release condition can be observed with the backlighted images. The experimental rig can be installed aboard the aircraft, which performs parabolic flights, and the flow of in the combustion chamber is supplied by the air and nitrogen bottles. The duration of the parabolic flights can be varied from the 21 to 33 seconds, which depends on the gravity levels. Each parabolic flight provides one test of the sample experiment of the one sample. And now, just imagine you are in the spacecraft. About the fire safety, the first question is about how can we know if there is a fire? And fire detector can help us to answer these questions. The fire detection system developed on Earth massively relies on the optical detection of soot particles, which are present in the smoke. In order to detect the fire correctly, it is thus important to know how their optical properties are affected by the gravity. As optical properties are related to their morphology, so in this part, I will present a new soot sampling technique with electrical wire, which are applied on a opposite flame spring. After the sampling and analyze, it seems that there is a big difference between the result soot particle sampled in microgravity, which present in the red color, compared to the soot particles sampled at normal gravity in blue color. And now we will check it together. How can we find it? An image here shows the flame in microgravity and at normal gravity. From the macro observation, we can find that the flame is more expanded and less bright, and also there are the smoke release at the chilling edge of the flame. About the situation in micro observation compared to the normal gravity, we can observe the soot particle which are more larger and also provide a different morphology in microgravity. Actually, the soot sampling in microgravity is not new, and it has been done with a flame over a burner. They have been found that the soot particle in microgravity also larger at normal gravity. It consists with what we found. But the big difficulty here that we have is to sample the soot particle with a splitting flame, which is the configuration closer to the real fire scenario. A video here shows the whole sampling process in microgravity. This video consists with the non-backlighted, backlighted, and subtract image. The electrical wire here will be ignited with the radiated heat provided by the igniter. And then an asymmetric flame will be generated. When the flame can propagates steadily, we will introduce an electric field to perform the Seuss sampling. A brass plate with the 5 TEM grease is fixed face to the flame so that the collected Seuss particle can be observed under the transmission electron microscope. And now let's see the sampling in detail with a series of the image here. The yellow rectangles represent the position of the TEM grease. We can observe the Seuss particle move towards the plaque because of the electrical field is presented, and the flame blanks and points to the fourth grid. At this position, a number of the Seuss particle can be generated under the electrical field. If we perform the same sampling under the same sampling conditions at normal gravity, we can find that the flame blanks less because of the nature convection, and this time the flame points on the third degree. After that observation, we can find that this sampling technique is intrusive because of the electrical field, but the gravity is still the only variable between these conditions. As the flame can burn differently because of the gravity, it can affect the result at different positions along the flame axis. So when we compare the result later, it should be based on the overall evolution of the different Seuss particle morphological properties along the flame axis. After the microscope observation, a series of the TEM image can be generated. And then to extract the information from the Seuss particle, we need to analyze these images. In this context, I feel grateful to work with Antoine Bordino, who did his such internship with us during my PhD period. And he worked especially on the TEM image analysis. And firstly, to analyze the image, we need to identify all the Seuss particle on the image. And then here we apply the method of the k-mean segmentation, who's proposed by the Spigen and the Rogate. For obtaining the result properly, they proposed pre-processing of the image with the 3 feature layers, which are the noise layers, texture layer, and the binary layer. And then applying the k-mean segmentation to this image composed of these 3 feature of layers, at the end, the Seuss particle can be properly identified. This method has been applied on all the TEM image that we obtained with a magnification range from 1,200 to 60,000. Now, the most intuitive results are the two-dimensional density of the Seuss particle on the image, and also the project area of the individual Seuss particle. The result about the density is plotted as a function of the flame axis. The red and blue color represent the result in micro and normal gravity. 2 highlight zones here correspond to the position where the flame blends with the electrical field. According to the evolution of the result, we can find that the density values are lower in microgravity than at normal gravity in the flame, and this turn is reversed at the trailing edge of the flame. This observation correlates with the heavy smoke release in microgravity than at normal gravity. And the projector area results can represent the size of the Seuss particles. The results are represented by the histogram, and each plot corresponds to each grid position. So the whole figure here represents the vertical flame. Based on the result of the median values, we can find that the Seuss particles sampled in microgravity are much greater than at normal gravity. If we estimate the Seuss particle residence time with the flame length and the flow velocity, we can find that the residence time is 3 times longer in microgravity than at normal gravity. The two other properties are the radius of the duration and also the fractal dimension. They are represented as the same way as the result of the area. The radius of duration can be represented also to the size of the particle, and it allows us to confirm that the soot particles sampled in microgravity are much larger than those sampled at normal gravity. As the soot particles sampled at normal gravity are more like the small spherical particles, and those in microgravity are fractal-like. So the fractal dimension analysis is just applied for those soot particles sampled in microgravity. When the value is higher, the soot particles are more like the densely packed aggregate. Otherwise, they are more like the chain-like branching aggregate. With the evolution of the result, we can find the transition from the densely packed aggregate to the chain-like branching aggregate along the flame axis, from the leading edge of the flame to the chilling edge of the flame. And the last property that we observe here is the soot primary particle size. Image A shows an example of the detection. Includes the 3 different ways to detect the primary soot particles. Firstly, using the age of the soot particle for the detection, and then the primary soot particle inside the age we can identify with the color gradient and also the entropy filter. It should be noticed that our objective is not to detect all the soot particles because of the overlap problem. Our objective is to use this method to detect most of them. Once the soot particles are identified, we can do the same plot as the previous result, and we can find that the soot primary particle size is greater also at normal gravity, and they provide property which is most polydispersed than at normal gravity. Now we observed overall the morphological properties about the soot particles sampled in microgravity and at normal gravity. We found a big difference between them. As detector present in ESS now are designed and calibrated based on the fire data at normal gravity, this difference may affect the fire detection accuracy in microgravity. Well, after the discussion on the micro-observation in microgravity for the fire detection, we can find that it needs a solid understanding about the flame, about the and also the combustion in reduced gravity to contribute a solid fire safety for the spacecraft. It should be the same thing for the partial gravity case, which means the gravity between the 0 to 1g. However, the experimental results in partial gravity are even less than at normal gravity, and also the microgravity. And for the first time, we apply the electrical wire sample in partial gravity, and then we can discover a cyclic period that has been never observed. And in this part, we are going to see how can we discover this phenomena. A video here shows the flame spread in different gravity levels. After the same ignition system, it can be generated a flame also in different gravity levels. In the increase in gravity, the flame becomes more stretched due to the addition of the natural convection, and also there are less the smoke release. Because it changes the thermal loss contributed by the particles, which correlates to the fuel release velocity. And then if we focus on the melting droplet upstream the flame, we can find that the dripping phenomena is stronger, and also there are more the chance to have a leakage of the droplet, as we can see here. And we are going to discuss about just the situation in Martian gravity, because it allows us to have a leakage of the droplet, and also this droplet slides not too far away. A sequence of the backlighted image and the infrared image allows us to illustrate this phenomenon. If we focus on the first cycle, we can see that the droplet slides far away from the flame at the beginning, and then it slows down so that the flame can catch up the flame later. And it does the same thing for the second cycle. The infrared image here allows us to extract the temperature of the droplet for the further analysis. Another videos allow us to better illustrate that we've identified the flame position and also the droplet position. It consists with the backlighted image, infrared image, and also the variation of the infrared signal. So it shows what we described in the previous slide. And now, if we want to study this specific cyclic flame sprays, we try to define the different spreading characteristic with the backlighted, backlighted and infrared image here for checking about the flame form position, droplet form position, and also the droplet temperature. And then also from the shape of the droplet, we can extract their contact angles information. And if we plot all these characteristics as a function of time, we can have this kind of the figure. On the left axis, it shows the characteristic about the position, and on the right axis, it shows the characteristics about the temperature and the angle. If we focus on the result about the flame form position, we can find that the flame can spread at a nearly steady rate. And about the other characteristic, they all display a periodic behavior. It should be noticed that the temperature of the droplet is always greater than its melting point. It means that they are always in the liquid phase. Now, to better understand the mechanism, we will focus on the one single cycle. As the flame sprays can be drying by the droplet, so in this cycle, its shape is showing here, and the droplet slides from the right to the left side, and the height of the droplet decrease at the beginning, and then it increase. The change of the droplet shape can be related to the gravity and the surface tension. The figure shows two examples here about the droplet shape. When the droplet has diameter larger than the smaller than the capillary length, the shape will be governated by the surface tension, forming spherical cape shape. And if it has the diameter larger than the capillary length, the droplet will be flattened by the gravity, and its height will reduce. A similar analysis can be applied to our droplet. If we plot their characteristic length and the capillary length of the same plots as function of the time, we can find that the capillary length is in the same order as the width and the height of the droplet. Another way to study the competition between the gravity and the surface tension is to calculate the Bond number, which is the ratio of the gravity to the surface tension. From the plot, we can find that this number is always slightly over than 1, which means that the effect of the gravitational force is slightly more permanent compared to the surface tension. And to have a more complete investigation, here we have force balance applied to analyze the droplet motion. And this droplet motion is driven by the gravitational force, adhesion force, viscous force, and drag force. It should be noticed that if we plot the velocity as a function of the time, we can find that the droplet slides almost over all the cycles, and then at the end, it tends to accelerate again. In the meantime, the droplet volume decreases at the beginning of the cycle and then increases again until the end of the cycle. Based on the above information that we obtained here, we can calculate the force, and they are plotted in here as a function of the time. On the left axis, it shows the gravitational and the adhesion force, and on the right axis, it shows the viscous force. As the drag force is much smaller than the other forces, so it is not plotted on this figure. And about the other characteristics may help us to further understand the mechanism. So it's also showing here. Based on the above information, we can find that the viscous force is dominant at the beginning of the cycle. As the droplet slide and the viscous force reduce, the gravitational force starts to dominate the droplet dynamics at the end of the cycle. Now we know a little bit more about the mechanism. So we try to also analyze this cyclic behavior under different oxygen content. The first characteristic that we check is the cyclic period. We have been finding that it decreases with the oxygen content. And now we try to understand the reason behind. As we know, the oxygen content can be affect the reaction of the flame. So we plotted we extract the flame spread rate, and we find that it decreases with the oxygen content. And also, another important information is about the droplet, how far the droplet can slide. So we extract the droplet travel distance in a cycle. We find that it decreases also with the oxygen content. Based on the information that we can have here, we can obtain a characteristic which can represent the time that the flame needs to catch up with the droplet. And based on this information, we can understand that the cyclic period decreases with the oxygen content because of the increase in flame spread rate, and then the flame makes the flame needs less time to catch up with the droplet. The similar analysis can be applied for the effect of the pressure, and we can find that the cyclic period is also decreases with the pressure, but this time the flame spread rate is not much affected by the pressure. Still, the droplet travel distance decreases with pressure, and also the characteristic time reduces with the pressure. As the flame spread rate is not much affected by the pressure, which means the effect of the pressure is not based on the same reason as the effect of the oxygen. As we know, the variation of the pressure can affect the heat exchange from the droplet and the surrounding environment. Now we try to check the temperature of the droplet. We find that the droplet cools down differently when we increase the pressure. That's why we extract a characteristic, which is the droplet temperature drop rate, and it decreases with the pressure. So the viscous force in this time, it increases with the pressure, so that the droplet slides less far than the low pressure. As a result, the cyclic period decreases with the pressure. And now the result that we discussed in this section shows the interesting observation which are not really expected, and the result may serve for the database for the future fire safety design about the space exploration. And we can find that we can feel that from the observation to understanding, then to the application, actually it takes time. However, the increase in the space exploration missions poses a big challenge for the technology improvement. As the fire safety concerns are not just specific to the space exploration, the inspiration can be found in the existing solution from the other industry. The intumescent flame retardant may be a solution to enhance the fire-resistant properties to the material. And yes, from the result, the simple result here about the extinction limit with the two different kind of the flame retardant, we can see that compared to the pure polyethylene material here, the flame retardant may help us to inhibit the flame propagation. And now in this section, we are going to check it together if it's really work also in the microgravity environment. And this time we apply the sample configuration without the without the metallic core in order to simplify the construction of the theoretical model and also the analyze later. A video here shows a comparison between the pure polyethylene material and the flame retardant loaded in polyethylene at normal gravity. The flame retardant expand when they are exposed to the external heating, and the expanded char layer can inhibit the flame sprays by slowing down the heat and mass transfer between the gas and the condenser phases. The intumescent can be obtained by a series of the reactions such as AP in the middle of the radio, or using the mechanical expansion such as the EG on the right side of the radio. Two figures here shows the post-combustion residues of these two flame retardants, and about the AP residues is internal structure is forming with small and large voids, and the cohesion of structure is relatively high. And for the EG residues, cohesion of the structure is high enough to provide thermal protection, but it is not strong as the AP residues. According to the result at normal gravity, we can find that the flame retardant can provide a higher extinction limit and also reduce the flame spray rate. As the heat and mass transfer change in a non-buoyancy environment, here we may ask the question if it is really efficient also in a percent of the gravity. To answer this question, the experiments with the AP and EG loaded in polyethylene samples are tested in normal and microgravity to study the extinction limit, flame spray rate, and also the smoke emission in the varying of the oxygen content with fixed pressure and flow velocity. Obviously, we start by looking the extinction limit, the upper for the normal gravity and below for the microgravity, and the circle and the cross marks represent the propagation and extinction conditions. And it has been found that at normal gravity, the flame retardant have a noticeable impact on the flame extinction. A schematic here of the flame retardant may further explain the mechanism behind. At the leading edge of the flame, the addition of the flame retardant can slow down the local pyrolysis rate, and which can of the solid fuel, which can influence the overall pyrolysis rate and also the flame spray rate. And the intumescent downstream can block a part of the heat from the flame, which weakens the pyrolysis process and also contributes the mitigation of the flame spray. When this performance is high enough, it can even stop the propagation. Moreover, the AP flame retardant provides a higher performance because the structure of the EG residues is not strong enough. Different to the normal gravity, in microgravity, the flame retardant do not improve the extinction limits. Worse, the EG loaded sample, they provide lower extinction limit compared to the pure polyethylene. A schematic here may provide a possible explanation is that the intumation acts as a polar media in the condensed phase, then driving the fuel towards the flame through the capillarity. This mechanism is shrouded at normal gravity because of the dripping, but dominates the viscous flow in microgravity. In addition, the absence of the convection flux prevents the blow off at the leading edge of the flame, and also from the air, increased air velocity due to the buoyancy. Well, for those conditions with the flame propagation, their average flame spread rate is plotted as function of the oxygen, and different color represent the different type of the sample. Micro and normal gravity represent the result in micro and normal, represent by the square and the circle marks here. And this figure is really dense, but the main information will be shown on the right side of the slide. And firstly, we have been find that for both gravity levels, the average flame spread rate increases with the oxygen content. As it is expected because the increased temperature of the flame enhances the heat transfer to the sample surface. And secondly, at normal gravity, the average flame spread rate decreases with the EG and AP flame retardants loading. As we mentioned before with this same schematic, in the addition of the flame retardant can slow down the pyrolysis process, and also the intumation acts as a heat barrier from the flame, so that it can slow down the flame spread. And the increase of the flame retardant loading can enhance this performance. About the situation in microgravity, with the backlighted image here of the pure polyethylene, we can observe it has the tendency to release twin droplets here, which slows down the propagation because the melting fluid cools down the upstream of the flame, increasing the heat loss. As the flame retardant is added, this process is not observed anymore, which can increase slightly the flame spread rate with the lowest flame retardant loading compared to the pure polyethylene. As this loading is further increases, the reduction of the flame spread rate can be observed again. So as a result, in microgravity, a higher flame retardant loading is required to reduce the flame spread rate. About the last point is, for the both gravity levels, the average flame spread rate for the EG loaded sample is lower than for the AP loaded samples. And this result needs a further experiment to explicitly understand the reason behind. As we said, the smoke can be a damage for the crew members. So the result of the smoke emission are reported here for the both gravity level. The smoke emission condition can be evaluated with the backlighted image. It is represented with the circle marks. For those conditions without smoke release, it is represented with the cross marks. Firstly, we observe that at normal gravity, the smoke emission is not reported for all flame retardant samples. Based on the backlighted image here, at normal gravity, we can observe a flame which is more stretched and brighter. It pointed to a decrease in soot residence time and higher local soot temperature, which leads the complete soot oxidation at the trailing edge of the flame. And secondly, in microgravity, the smoke emission increases with the flame retardant loading. One of the explanations can be found from this figure. The gaseous fluid pyrolyzes from the solid fuel. should be flow through the intermission region and then reach the trailing edge of the flame, which promotes the production of the soot particle in the flame, and thus increasing the smoke release. Moreover, the EG expansion creates the graphic runs from the by the rapid sublimation, which also promotes the carbonaceous element. It can be released from the flame and increases also the smoke release. And on the other hand, about the AP expansion, which can be driven by the carbonation mechanism, is also promotes the smoke emission. For the last point, in microgravity, the increase of the EG loading caused the smoke emission transition at lower oxygen content, as you can see here. If we compare the flame retardant at the same loading, we can find that the EG samples produce a larger intermission region, which leaves a longer residence time and increase the chance to have smoke release. Moreover, its cohesion of structure is not strong as the AP residues, so it can be anticipated that the carbonaceous matter can be released at a higher rate from the EG loaded sample. And the difference result in the different gravity levels can remind us that it needs more the experimental observation before employing the flame retardant for the spacecraft design. About the conclusion, not just about this presentation, but also my thesis. For the first part about the soot sampling, we developed a new sampling technique, and we observed the soot particles are greater in microgravity than at normal gravity, and they are more fractalized and polydispersed in microgravity. And in partial gravity, the flame sprays in partial gravity are characterized with the extinction limits and the flame spray rate. This part of the result is not presented here, but it is still in my thesis. And also the cyclic flame sprays in Martian gravity are observed and analyzed. About the last part, the intermission flame retardant are firstly experimented at both normal and microgravity. Their extinction limits, flame spray rates, and smoke emission are characterized. And each path has their perspectives. About the fire detection, a detector will be installed in our experimental rig diamonds, which allow us to measure their size, oxygen concentration, and also typology of the particles. And about the soot sampling, we can apply the new TEM method to have a better observation about the morphology of the soot particles and even extract their 3D properties. And for the partial gravity, we can test the concurrent flame spray, which is configuration that closer to the real fire scenario. And we can also test the flat sample configuration, which is the most experimented in microgravity, so it could allow us to do the comparison later. And the cyclic flame spray can be used to validate the numerical tools, which is being developed by Jean-Louis Consalavi at Aix-Marseille University. And for the last part, different type of the flame retardants have been tested in microgravity for finding a best formula. And then the flame retardant can be loaded in electric wire for the application. And thanks for your attention. And here I put just examples of the experiments which was not really expected, but here it can remind me that in the reality we cannot really get what we want, but those unexpected things makes the science progress. And yeah, that's it. Thanks for your attention.